Everyone, ready for another deep dive? You guys sent in some awesome stuff on gravity from Wikipedia's gravity entry, and I am super pumped to dig into this with all of you.
Yeah, it's one of those things we kind of take for granted, Like it's just there.
Totally. But there's so much more to it than meets the eye. It's this, fundamental force that shapes the entire universe.
Absolutely. And our understanding of it has evolved like crazy over time.
That's what we're going to unpack today.
Yeah.
So to kick things off, let's go way back to, ancient Greece. Aristotle had this idea that Earth was the center of everything.
Right. Everything was drawn to it.
But even back then, not everyone was buying it, right?
Yeah, there were some skeptics. Like Plutarch, he was like, wait a minute, is Earth really that special? Maybe all objects attract each other, not just to Earth.
I love that.
Yeah.
Even back then, they were debating the nature of gravity.
For sure. Those early philosophers were really onto something.
So how did we move from philosophical ponderings to actual experiments? When did science really enter the picture?
Well, we got to fast forward a bit to the scientific revolution. Around the mid-1500s, scientists started, putting those old assumptions to the test.
So they weren't just thinking about it anymore. They were actually, doing stuff.
Exactly. They were experimenting.
Give us an example. What kind of experiment are we talking about?
Okay, picture this. You're in the Netherlands in 1586. Simon Stevin is up on top of the Delft Tower. He's about to drop 2 cannonballs.
Okay, I'm listening. One heavy, one light.
Exactly. The big question was, would they hit the ground at the same time?
Oh, that's a good question. I'm genuinely curious. What happened?
They landed simultaneously, boom, same time.
Whoa, so the heavier one didn't fall faster?
Nope. That was a major turning point. It basically proved that an object's weight doesn't affect how fast it falls, well, at least not in a vacuum.
Right. So air resistance is a factor, but gravity itself is treating all objects equally.
Exactly.
That is so cool. So this kind of set the stage for the big name that everyone associates with gravity.
Isaac Newton.
The one and only.
Yep. In the 17th century, he came up with this thing called the law of universal gravitation.
Oh, I've heard of that. It's a big deal, right?
Huge. It basically says that every object in the universe attracts every other object.
So it's not just about stuff falling to Earth anymore.
Nope, not at all. Newton showed that gravity was a universal force. It's acting between, planets, stars, everything. And the strength of that attraction depends on 2 things: the mass of the objects and the distance between them.
Okay, so the more massive the objects, the stronger the pull.
Exactly. And the farther apart they are, the weaker the attraction.
Got it. So it's this intricate dance of mass and distance.
It is. The whole universe is doing this cosmic dance thanks to gravity.
This is blowing my mind. Didn't Newton's theory even lead to, the discovery of a new planet?
You're thinking of Neptune. Astronomers had noticed these weird wobbles in Uranus's orbit.
Ah, so something was off.
Yeah, it was like something was tugging on it. Newton's theory couldn't fully explain it, but they used his equations to predict that there was another planet out there, Neptune, causing those wobbles.
And they found it.
Boom! Exactly where the math predicted it would be.
That's so wild. So his theory wasn't just, an explanation. It had predictive power.
Yeah.
That is amazing. But I have a feeling things are about to get even crazier as we move into the 20th century. Enter Einstein.
Einstein, he completely revolutionized our understanding of gravity.
I know, right? But I got to be honest, the concept of space-time, it still kind of boggles my mind.
Yeah, it's definitely one of the most, mind-bending concepts in physics. Einstein basically said that gravity isn't a force, it's a warping of space-time itself.
Okay, hold on. Warping of space-time, it's a lot to, process. Can you give me an analogy?
Sure. Picture a bowling ball on a trampoline.
Okay, I'm with you.
It creates a dip in the fabric, right? That's kind of like how massive objects like stars warp space-time around them.
So planets aren't being, pulled towards the sun. They're actually just following the curves in space-time caused by the sun's mass.
Exactly. It's like rolling a marble on that trampoline. It'll curve towards the bowling ball, not because there's a force pulling it, but because it's following the contours of the warped fabric.
Okay, so it's not about some invisible force. It's about the shape of space-time itself.
Exactly.
But is there any, proof that space-time actually warps like this?
There is. One of the coolest pieces of evidence is something called gravitational lensing. Basically, light from distant stars gets bent as it passes by massive objects like galaxies.
Whoa. So we can actually see the effects of this warped space-time.
Yep. This bending of light creates these distorted images of the stars. It's like a cosmic mirage.
It's incredible. So we've come a long way from, Aristotle and falling cannonballs,
We
right?
have. But even with Einstein's genius, there are still mysteries surrounding gravity, things we're still trying to figure out.
Oh, I love that. Even with all our knowledge, there's still so much we don't understand. So what are some of these, like, modern-day gravitational puzzles?
One of the biggest challenges is trying to reconcile general relativity with another huge part of modern physics, quantum mechanics.
Right. I've heard of quantum mechanics, but I don't really get it.
It's pretty complex, but basically, these two theories describe the universe in very different ways, almost like different sets of rules.
So the universe is playing by two sets of rules.
That's the problem. General relativity is all about gravity being smooth and continuous, but quantum mechanics deals with the very small, where things are like chunky and jumpy.
Chunky and jumpy, I like that. So it's like trying to fit square pegs into round holes.
Kind of, and that's where the idea of quantum gravity comes in.
Quantum gravity, is that the key to uniting those two sets of rules?
Exactly. It's one of the biggest mysteries in physics right now, the search for a theory of everything that would bring gravity and quantum mechanics together.
A theory of everything. That's like the holy grail of physics. But for now, let's bring things back down to Earth. Literally. I want to know more about our planet's own gravity.
Sure. So Earth's gravity is actually a result of two forces: the gravitational attraction between objects and the centrifugal force caused by Earth's rotation.
Oh yeah, centrifugal force. I remember learning about that. So
Mm.
does that mean gravity isn't like the same all over the planet?
You got it. It's actually a little weaker at the equator because of that outward centrifugal force from the Earth spinning.
That's a fun fact. I never knew that.
Yeah, it's not a huge difference, but it's there. But hey, now that we've talked about Earth, want to zoom back out into the cosmos, there's this really awesome thing called gravitational waves.
Oh yeah. Didn't we actually detect those like a few years ago?
Yep. In 2015, this observatory called LIGO made history by directly observing gravitational waves for the first time.
Whoa, so these are like ripples in space-time. What caused them?
The collision of two black holes billions of light years away.
Black holes colliding. Okay, that's officially the coolest thing I've heard all day.
Right. And this detection not only proved that Einstein was right, it also gave us a whole new way to study the universe. We can actually hear these events that we couldn't see before.
That's mind-blowing. So we can learn about these invisible objects just by studying their gravitational influence.
Exactly. But I have a feeling even with all these advancements, there are still some gravitational anomalies out there. Things that don't quite fit with what we know.
Oh, I love a good mystery.
Why?
It's like what?
Well, there's something called the flyby anomaly.
Flyby anomaly. Okay, you got to tell me more.
It's basically this thing where some spacecraft have been observed accelerating a bit faster than they should during gravity assist maneuvers.
So there might be some like unknown gravitational effect at play.
Maybe. It just shows that we're still learning. And on top of that, there are even these alternative theories of gravity out there, ideas that challenge Einstein's whole framework.
Whoa, this is getting deep. What are some of these alternative theories?
Well, some of them are pretty complex and haven't been as successful in explaining all the things general relativity can, but they're still super interesting. They show how scientists are always questioning and pushing the boundaries.
I love that. It's like what we saw with Plutarch challenging Aristotle way back when. That willingness to think differently is what moves science forward.
Absolutely. And who knows, maybe someday one of these alternative theories will lead to another huge revolution in our understanding of gravity.
The possibilities are endless.
Exactly. But now, how about we shift gears a bit? I think we're ready to tackle those mind-boggling black holes.
Yes. Black holes. I'm so ready. Stick around, listeners. Things are about to get really gravitational.
So black holes, they're like the ultimate cosmic enigmas, right?
Yeah, they've always kind of freaked me out, to be honest. Like giant cosmic vacuum cleaners.
I know, right? But they're also super fascinating. They're one of the most extreme consequences of general relativity. Remember all that stuff about warped space-time?
Yeah, the bowling ball on the trampoline. That was a good one.
Right. Well, a black hole takes that warping to a whole new level.
Okay, so it's like the bowling ball creates this like infinitely deep hole in the trampoline.
Yeah.
And nothing can escape.
Exactly. It's a region of space-time where gravity is so strong that nothing, not even light, can get out.
Whoa. So how does something like that even form? What could possibly create that much gravity?
They form when massive stars die, like really, really massive stars.
Okay, so when a star runs out of fuel.
Yeah, it collapses in on itself. Imagine all that stellar material, all that mass getting squeezed into an incredibly tiny point.
Tiny. Like, how tiny are we talking?
We're talking a singularity. Essentially, it has infinite density.
Infinite density. That just sounds like wrong somehow.
Yeah, it's definitely mind-bending. And surrounding this singularity is something called the event horizon. It's basically the point of no return. Once you cross it, you're trapped. There's no coming back.
Okay, so if I were to fall into a black hole, hypothetically, of course,
Yeah.
what would happen to me? Would I just get, like, squished instantly?
Well, not exactly. It would be a way weirder than that. According to general relativity, as you get closer to the black hole, time would actually slow down for you.
Time would slow down.
Uh,
Whoa, that's trippy.
Yeah, it's like time dilation from, like, those sci-fi movies.
So I'd be aging slower than everyone back on Earth. That's kind of cool, actually.
And as you get closer to the event horizon, you'd experience something called, wait for it, spaghettification.
Spaghettification. What in the world is that?
Basically, the gravity would be so much stronger on your feet than on your head that you'd get stretched out like a really long noodle.
Oh, okay, maybe not so cool after all. So, black holes are terrifying and fascinating all at the same time. But how do we even know they exist? If they don't emit light, how can we see them?
We can't see them directly, but we can observe their effects on the stuff around them. For example, when matter falls into a black hole, it heats up like crazy.
Heats up like a lot.
A lot. And it emits X-rays, which we can detect with telescopes.
So we're not seeing the black hole itself, but we're seeing the stuff falling into it.
Exactly. It's like seeing the shadow of the black hole against the backdrop of space.
Okay, that makes sense. Now, remember how we were talking about Earth's gravity not being uniform?
Yeah.
Can we go back to that for a minute? I'm kind of curious about the details.
So remember that Earth's rotation creates centrifugal force. That force actually counteracts gravity a little bit. And this effect is strongest at the equator.
At the equator. Why there?
Because that's where the Earth's spin is the fastest.
Okay, so the faster the spin, the stronger the centrifugal force, and the weaker the gravity.
You got it. So you would actually weigh slightly less at the equator than you would at the poles.
No way. That is so cool. So it's not just the rotation that affects gravity.
Nope. There are other things, too, like differences in the density of the Earth's crust.
Whoa, so it's this whole, like, intricate system.
Exactly. And that's what makes gravity so fascinating to study. There are always these, like, subtle details and unexpected connections to discover.
Speaking of discovering new things, what about gravitational lensing? You mentioned it earlier. Is that, like, light bending because of gravity?
Bingo. Remember the bowling ball on the trampoline? Imagine if you rolled a marble past the bowling ball, it wouldn't go straight, right?
Oh, yeah. It would curve a little bit.
Exactly. Well, light does the same thing when it passes by massive objects like galaxies. The galaxy's gravity warps the space-time around it, so light from more distant objects gets bent as it passes by.
Whoa, so we actually see, like, distorted images of those distant objects.
Yep. It's as if the galaxy is acting like a giant magnifying glass. It's pretty wild.
It's like gravity's giving us a sneak peek at things we wouldn't be able to see otherwise. That's incredible.
And it's become a super important tool for astronomers. They use it to study the distribution of matter in the universe and even to search for dark matter.
Dark matter. Okay, that's a whole other can of worms. I've heard of it, but I don't really know what it is.
Think of it like this. It's a type of matter that doesn't interact with light, so we can't see it directly. But we know it's out there because of its gravitational effects.
So it's like a cosmic phantom, exerting its influence but remaining completely hidden.
Exactly. And gravitational lensing is one of the main ways we can map out where this dark matter is hiding.
I love how we can use gravity to unlock these secrets of the universe.
It's pretty awesome, right? It just goes to show how powerful this force is and how much we still have to learn about it.
Agreed. Well, I think we've covered a ton of ground today, pun intended.
Yeah, we've really dived deep into the mysteries of gravity, from those early Earth-centric ideas to mind-blowing concepts like black holes and gravitational waves.
And we've seen how our understanding has changed so much over time, but there's still so much we don't know.
Absolutely. The quest to understand gravity is far from over.
Yeah, and it's that constant sense of wonder and exploration that keeps science so exciting.
I couldn't agree more. Now, for our final segment, let's circle back to some of the big takeaways from our gravitational journey, and maybe even ponder some of the even bigger questions that gravity raises.
Sounds good to me. Stick around, listeners, because things are about to get really existential.
So, wow, we covered a lot of ground in our exploration of gravity. From those early ideas of the ancient Greeks to those mind-bending concepts like black holes and gravitational waves.
It's pretty amazing to think about how far we've come
Yeah.
in our understanding, like from thinking that everything revolved around Earth to like realizing that gravity is this fundamental property of space-time itself.
Yeah, it's been a pretty wild ride, right?
Totally. And along the way, we encountered some truly incredible phenomena like gravitational lensing. I mean, massive objects can actually warp space-time and bend light. That's just like, whoa.
It's like a cosmic magic trick almost.
Right. And it gives us this glimpse into these distant corners of the universe that we wouldn't be able to see otherwise.
And then there are those mysteries that are still out there, like the flyby anomaly and that quest for a unified theory of quantum gravity.
I love that even after all this exploration, there's still so much we don't know about this force that shapes like everything around us. It's humbling.
It is, and it's exciting. It means there's still so much more to discover.
Okay, so thinking about all this has got me wondering about some even bigger questions like, what's the ultimate fate of the universe? Is gravity eventually going to like pull everything back together in some kind of big crunch? Or will the universe just keep expanding forever?
Those are some big questions, and while we don't have all the answers yet, the evidence we have now suggests that the universe is probably going to keep expanding.
So it's just going to keep spreading out, getting colder and darker over time. It's kind of a bleak thought, isn't it?
It is. But it also highlights how precious this moment is, right? The time and space we inhabit. It's like a reminder to appreciate it and keep exploring it.
That's beautiful. I like that. Well, on that note, I think we've come to the end of our deep dive into gravity. I don't know about you, but I feel like I've learned a ton.
Me too. It's been a blast exploring all these fascinating concepts with you.
And with our listeners, of course.
Hmm.
It's amazing how these deep dives can take us from these ancient ideas all the way to the cutting edge of modern physics. And it all started with that Wikipedia entry on gravity.
It's proof that you can find incredible knowledge in unexpected places.
Totally. So keep
Yeah.
those curious minds going, folks. Never stop exploring. And who knows, maybe you'll be the one to unlock the next big secret of the universe.
Until next time, keep looking up and stay curious.